Our limit comparison test tells us that if we have some sequence here greater than 0 and another sequence, we'll call these a sub n and b sub n, another sequence which is also greater than 0, and this is true for all n greater than some n that's an integer, then one of three things is possible. If the limit as n approaches infinity of sequence A over sequence B equals some constant which is greater than 0, then either the series of A sub n and the series of B sub n are both convergent or they're both divergent. So they'll both either converge or both diverge if the limit as n approaches infinity of sequence A over sequence B equals some constant. Now this could be any constant greater than 0. The other possibility is that if the limit as n approaches infinity of sequence A over sequence B equals 0 and the one on the bottom, the series of the sequence on the bottom B sub n converges, then the series of A sub n also converges. So if the limit goes to 0 and the one on the bottom converges, then the one on the top also converges. Now notice what this doesn't say. If it goes to 0 and the one on the bottom diverges, we still don't know anything. So just keep that in mind. And there's a similar thing happening with case 3 here. The third possibility is that if the limit as n approaches infinity of sequence A over sequence B goes to infinity and the series of B sub n diverges, then we can say that the series of A sub n also diverges. So if the limit goes to infinity and the one on the bottom diverges, then we know that the one on the top also diverges. That's the third possibility. Now, our limit comparison test, this can be used to cancel undesired terms, and it's very useful in certain situations. So I'm going to give you a few tips here that will hopefully help you through this section. So the first tip for the limit comparison test, also sometimes referred to for short LCT, is that you should not confuse it with the ratio test. Because with the ratio test, if we have an outcome of 1, if the limit equals 1, then we'd have no conclusion. But with the limit comparison test, the outcome can equal 1. And an outcome of 1 can be conclusive. So don't let that confuse you with other types of divergence tests. The second tip is that it doesn't matter if B sub n is larger or smaller than A sub n. Now, a lot of textbooks will give you an example where sequence A is smaller than sequence B, but that doesn't necessarily have to be the case. It is the outcome of the limit comparison test that matters. So you can put either the larger one or the smaller one on the bottom to suit your needs. And that means that if you try the limit comparison test and something's not going right or doesn't look right, you can try flipping them around and then see if you are able to meet one of the cases that we looked at. The third tip that I have for you is that the one on the bottom, B sub n, this is going to be the known series. This is the one that we know whether or not it converges or diverges before we try our limit comparison test. So this should always be on the bottom. So your B sub n, it doesn't matter if you pick the sequence that is larger or smaller of the two, as long as that's the known series, that needs to be on the bottom. The converse is not always necessarily true. So if you put the known series on the top, you may get a conclusion that that might look okay, but it doesn't hold water. So let's do an example here. here we have the series. It's an alternating series from n equals 1 to infinity of -1 to the n. That's the alternating part. And then the non-negative part, or the positive part, or the non-alternating part, whichever way you want to think about it, is this ln of n over 4n plus 1. Now, we could use the comparison test and say, okay, well, this is going to be smaller than ln of n over 4n, and we could see whether or not that would converge or diverge based on our integral test. But let's use our limit comparison test here. Okay. Now, for starters, we have a alternating series, so we're first going to see if that meets our conditions for the alternating series test, and then we're going to use our limit comparison test to see if the non-alternating part would converge or diverge as a series, which would make it absolutely or conditionally convergent. So, our b sub n, this is the positive or non-alternating part. Our b sub n, let's say our b sub n is equal to ln of n over 4n plus 1. Now we can see right away that this is going to be positive. It's going to be positive because n is an integer. N is an integer greater than 1, so it's going to be ultimately positive here. We can also see that b sub n plus 1 is going to be greater than b sub n. And we know this just kind of intuitively here because this denominator here, 4n plus 1, this is a linear expression. So if you were to graph just the 4n plus 1 as a function, it's just going to be a straight line that's going to go straight up. And in contrast, our natural log function, it increases more slowly. In fact, it just kind of plateaus, and it starts increasing more slowly as you go along. So you could argue that this 4n plus 1 it's going to increase faster than the ln of n. If you look at it as a function of x, just imagine that the n's were x's instead. The denominator is going to start increasing faster than ln of n, and what you're going to have is each b sub n plus 1 term is going to be greater than the previous b sub n term. Now, we could also say that the limit as n approaches infinity of our b sub n is going to be equal to 0. And for this, you could use L'Hopital's rule. You could just change your n's to x's and think of it were a function. And let's just we could do this in our heads here. If you have the limit as x approaches infinity of ln of x over 4x plus 1, well, if you follow L'Hopital's rule, you would just get the you would just get the derivative of ln of x, which is just 1 over x, and the derivative of 4x plus 1 is just going to be 4. So that would boil down to 1 over 4x going to infinity, which would just go to 0. And if you don't believe me, or if all of that seemed like a lot to take in, just pause the video, get out a sheet of paper, and just work through it yourself to show that this expression here satisfies the conditions for the alternating series test. So we could say that this series is convergent. It's a convergent alternating series. This is a convergent. This whole thing is a convergent alternating series. But we still don't know whether or not it's absolutely or conditionally convergent. So let's just explore that a little bit. Imagine that we have a series that's just based on R B sub n. So we're thinking of a different series now. And this is just going to be the series from n equals 1 to infinity of just ln of n over 4n plus 1. Now this is just our non-alternating part, and we've just made it into its own series. Well, because we've added 1 here, the denominator has increased. So that means the value of the whole expression decreases when we add that 1. And this series is going to be less than the outcome of this series, which would be the series from n equals 1 to infinity of just ln of n over 4n. Okay, and we can see straight away that this is going to be a divergent series, as if you just do the integral test. If you do the integral test real quick here of 1 over 4, the integral from 1 to infinity of ln of x, our n's become x's, so this becomes a function, over x. We've already pulled our 4 out here, so instead of 4n, we just have x with the 1 over 4 out front here. And this is going to equal 1/4. We could just do a little u substitution here, and you see that the derivative of ln of x is just 1 over x. So we just have u du, and I like to think of these integration terms as u of 1 to u of infinity, and that way you know that you have to convert it back. So our ln of x was our u, and then our 1 over x is just our du. So this is going to be equal to, move everything up a little bit, this is going to be equal to 1/4 of, we'll just evaluate this is u squared over 2. That's just the integral of u. So just following our power rules of integration. And this is from u of infinity. Sometimes you might see it as t approaches infinity, but I like to just go ahead and jump to the chase here and just put infinity, since we are in fact dealing with infinity. U of 1. And this is going to equal, and this is going to equal, well, we could say that our 4 times 2 is just going to be 1/8. But before we do that, let's go ahead and write it the way that I explained. You might see it this way sometimes in your textbook. So this is the limit as t approaches infinity. We're just going to plug back in for our u, 1 over 8. And our u was ln of x. So that this u squared here is going to be ln squared of x. And this is from x equals 1 now to t as t approaches infinity. Well, you can see from our upper bound that the the natural log of e to get to infinity, well, that's just going to be infinity, and of course infinity squared is just infinity. So this whole thing is just going to go to infinity. Now notice, we know that this diverges, but we don't know if the smaller series diverges yet. We still have to prove that. So in order to do that, we're going to do our limit comparison test. We're going to do our limit comparison test here. So just get section this off here. We've shown that the greater series is divergent. So with our limit comparison test, we can say that ln of n over 4n, let's let this equal our b sub n. This is our known series. We know that this diverges as a series. And let's let our a sub n equal this sequence here. So ln of n over 4n plus 1. This is going to be equal to our a sub n. So our comparison test tells us that we need to set it up this way. We have the limit as n approaches infinity of our a sub n over b sub n. And if this equals some constant, doesn't matter if it's 1 or whatever, as long as it's greater than 0, then they're both either going to be, both the series are going to be convergent or divergent. Let's do that. Okay. So we have the limit. Let's start down here as n approaches infinity of ln of n over 4n plus 1. I like to kind of write the fraction as a fraction of slanty fractions so that we can see straight away what we're working with. Some people like to invert the fractions and multiply them together, and I'm a fan of whatever works. But there's an n there. But I like to keep one directly on top of the other so we can really see what we're working with. This is ln of n over 4n. And this is the limit as n approaches infinity of the two. So straight off we can see that our ln of n's are going to cancel, and we are going to be left with the limit as n approaches infinity of 4n over 4n plus 1. And as n approaches infinity, this plus 1 is going to become increasingly insignificant, and this is just going to go to 4n over 4n, so this is just going to equal 1. And just like we said in our definition, if it goes to some constant, and 1 is a constant, doesn't matter what it is, then either both the series are going to converge or they're both going to diverge. So if the bottom one diverges, then the top one diverges. If the bottom one converges, then the top one converges. So this equals some constant which is greater than 0. So therefore we can conclude that the series from n equals 1 of negative 1 to the n of ln of n over 4n plus 1, this is conditionally convergent. This is only conditionally convergent. Okay. Now notice a couple of things. When we did our alternating series, you could have stopped here, but this would have only been partly true. You could say, oh, this is a convergent alternating series, and you would have been right. But you still wouldn't have shown whether or not it is absolutely or conditionally convergent. And notice that our hypothesis in the beginning that, maybe we could have just used the comparison test and then the integral test. And you're right, if this were convergent, then we would be able to prove that, this would also be convergent because this is greater than this. But because we did our integral test and we showed that this was divergent, then we still didn't know what the outcome of this. And the only way that we could have had that outcome is by the limit comparison test. So I hope that you have found this useful.